Let's take a look at the topic of differentials. So the first question to ask is, what is a differential? So the expressions dx, dy, and dz, which can also be written df, and these are infinitesimals, which we also refer to as differentials. Now, you've certainly encountered these expressions before, but you may not have thought about what they meant or discussed what they meant. So they're best understood as very tiny changes in the variable. So when we talk about change, what do we mean? Well, we understand a change like delta x very well. So a couple different ways. So if you have a formula or a table of values, delta x would be the difference between two x values. You might write it as x2 minus x1. On a graph, it could be, if you have 2 points, it would be the length of a segment that is on or parallel to the x-axis. So the differential dx is something different. So that's visible on a graph after zooming in, quote unquote, all the way. And in a formula, you could see it by taking delta x and shrinking it to a single real valued point. So we talk about these things being infinitesimal. They're infinitesimally small. So ratios of differentials represent rates of change. So we've previously, in single variable calculus, y equals f of x, we can write the derivative as dy over dx. So now, if y is constant, then we can write partial df dx as the rate of change of the function f of xy with respect to x. So these are some of the notations, kind of an idea about what we mean when we talk about differentials, if you haven't seen it before. And let me just mention, that's just the basic idea. The full theory behind differentials and infinitesimals is beyond what we're going to talk about. Okay. So now that we understand a little bit about what we mean when we say differentials in general, all these d expressions. So the equations for linear approximation can be written with deltas and differentials. And let's see what that gives us. So we're going to write down a couple different things. We're going to write down, first of all, equations for linear approximations. And then we're also going to write what this looks like. First of all, we're going to write what this looks like in 2 dimensions for y equals f of x, and if we're at the point AB. So some of those should be pretty familiar. We're also going to write these expressions down in 3 dimensions, meaning when you have z equals f of xy, and we're at the point ABC. Some of those will be familiar, and some of those will be new. Let's take a look. So first of all, let's write these things down without differentials. So without differentials, a linear approximation could look like y minus b is approximately f prime of a times x minus a. That's just our good old, one of the forms for the equation of a tangent line. Now we have the 3-dimensional version of linear approximation. Z minus c is approximately f sub x, so the derivative at the point AB times x minus a, plus f sub y, so that derivative at the point AB, times y minus b. So this is something that we talked about recently with linear approximations, but now in 3 dimensions. So now let's rewrite these formulas, but instead let's write them down using deltas. So we recognize that y minus b is really just a type of delta y. It's a change in y values. So this is the 2-dimensional version. And f prime of a, and then x minus a, we can just reinterpret as delta x. It's a change in x values. Okay. Now let's hop over to the 3-dimensional version. So once again, noting that we often interchange when we're at z equals f of xy, we can write z and f kind of interchangeably. So either delta f or delta z would be approximately f sub x, that derivative at the point AB, times delta x, plus f sub y, that derivative at the point AB, times delta y. And again, remember that because we're moving from one point to another point, assuming that the rates or the derivatives are constant, is only an approximation. But now, suppose we shrink down to a single real point. We can make these statements exact. And they're exact if we use d's or differentials. So now we have, so just take the delta statements and turn them into d statements. dy equals f prime of x dx. And of course, if we get rid of our prime notation, we can just write dy equals dy over dx times dx. Now take a look at that for a second. When you write it like that, it's kind of obvious that that's true. It's dy equals dy over dx times dx. You can think of the dx as canceling and then just dy equals dy. But of course, we know that we can take dy over dx and reinterpret that. If y is a function of x, we can reinterpret dy dx as the derivative function. Okay, so that's the two-dimensional version. Now let's kick it up to the three-dimensional version where we have z equals f of x, y. So what do we have? So taking those delta statements from above and turning them into d statements. And now we're going to use, we're not going to use f sub x for the derivatives. We're going to write everything in terms of d's. So we can say that dz equals partial dz dx times dx plus partial dz dy times dy. And again, notice how we're just translating those directly from delta statements into d statements. And then using our alternate notation for derivatives, we could write this, and using f instead of z, we could say df equals d sub x of f over dx times dx plus d sub y of f over dy times dy. And what is this saying in words? So in words, first let's look at the two-dimensional y equals f of x case. That just says, either in the approximate case or in the exact case, the change of the function, delta y or dy, is its rate of change times the change in the variable, which would be f prime of x times dx in the exact case. Now let's kick it over to the three-dimensional case. Notice that there are two terms. So let's break this down. The change in the function is its rate of change in the x direction times the change in x, that's dz dx times dx, plus its rate of change in the y direction times the change in y, and that's partial dz dy times dy. And of course, we could also write that as deltas as an approximation. So just as a little reminder, how we sometimes use this in formulas, if you have the equation, say in single variable calculus, y equals x squared. So we can write this as a derivative statement, dy over dx equals 2x. Now we can also turn this around into a differential or a change statement, which would be dy equals 2x dx. So notice that mathematically those two last equations are equivalent. It's just that one quite literally is written with a fraction, with a division, and the other one's written with multiplication. One represents a rate, and the other one represents a change. So now there's a little more complexity in multivariable calculus for z equals f of x, y, because there's more than one input variable. So when we talk about changes, we have to be explicit about which change we're talking about. We're talking about derivatives, we have to be explicit which derivative we're talking about. So there's some different, so we've seen one or two notations for this. Let's talk about a couple other notations. So another notation is to write it like this. So df equals d sub x of f plus d sub y of f. What does this say in words? The change in the function equals the change in the function due to x plus the change in the function due to y. Now, in each term, if we simply divide, well, in the first term on the right side, divide by dx, multiply by dx. What does that give us? df equals df dx times dx, excuse me. And then same thing, and similarly in the second term, plus df dy times dy. And that's the rate of change in the x direction times the change in x, plus the rate of change in the y direction times the change in y. And we're adapting this notation from our notation from just linear functions, where we said if we have a change in a linear function L, we can break it down in two parts. That's just the delta sub x of L plus delta sub y of L. And now we've adapted this from deltas to d's, where if we consider these things infinitesimally, we can still take, it's no longer an approximation, these rates are in fact exact. Now, a side note for something that I'm just going to mention in passing, and we're going to use it not now but later. We can write this in vector notation. So notice that when we're writing down df, it's something times something plus something times something. That should sound familiar. From vectors, that's just a dot product. Let's write down what we're taking the dot product of. So df is just the vector df dx comma df dy dot the vector dx comma dy. Okay, I'm just mentioning that in passing. We're going to put that in our pocket, and we're going to use it later. Okay. Now let's try to do a little calculation. So for this function, f of xy equals x squared y cubed, let's calculate what is df. So we just go to our formula. We know that df is just partial df dx times dx plus partial df dy times dy. So we just need to calculate the two partial derivatives. So partial df dx is 2xy cubed. Partial df dy is just 3x squared y squared. And then just plug that in. So df equals 2xy cubed times dx plus 3x squared y squared times dy. So for now, we can just think of this as a formal calculation. We're going to be using this more extensively later on. But one thing I do want to go back is talk about the connection. I want to do another problem that emphasizes the connection between the approximation using deltas and this exact statement using d's. So now let's take a look at this next problem. There we go. Okay. So for this function, f of xy equals y squared e to the x plus x. Clear. Okay. So first, find df. Now, at the point 0, 2, 4, we're going to do a bunch of other stuff after that. So let's get into it. So first of all, we have that df equals, so first we need to find partial df dx. So actually we're going to need partial df dx quite a lot so in this problem, so let's just write that down on the side. So df dx is just y squared e to the x plus 1, and then df dy equals 2y e to the x plus x, it looks like a constant, so the derivative is 0. So there we go. Okay, so now let's write down df. So now we have the df equals y squared e to the x plus 1, all of that times dx, plus df dy, which is 2y e to the x, all of that times dy. So there's that bit. Okay, now, from now on, we're going to be at the specific point 0, 2, 4. So let's take a look. So first, let's find the linear approximation function, L of xy equals. So first of all, we need the original value. The original z value is c, which is 4. So it's 4 plus. Now I've got the two change terms. So first, it's going to be the derivative evaluated at this point. Oh yeah, I should have. Sorry, let me reorganize. I should have put that in. So let me just take a moment and rewrite that over here. So df dx 1 df dx at 0 to 4 equals 2 squared e to the 0 plus 1, and that's just 5. And then df dy was 2y e to the x df dy at the point 0, 2, 4 is just 2 times 2 e to the 0. Work that out and you just get 4. Okay. So now I just put all this work on the other side. So we need the rate in the x direction. We just calculated that at this particular point. That value is 5. And now we need x minus a. So that's x minus 0. I'll just leave the minus 0 in there to make it look like the formula. And then we need the rate in the y direction, which is 4, times y minus b. That's y minus 2. So we could clean that formula up if we want. We don't need to. I'll just leave it like that. Okay, so there's our linear approximation. So now, so part C says, use L to approximate the value of the function at 0.2, comma 2.1. So f of 0.2, 2.1 is approximated by the linear approximation function. So that's L of 0.2, comma 2.1. Let's plug it in and see what we get. So that, actually, so plug it in and we get 4 plus 5 times 0.2 minus 0 plus 4, 2.1 minus 2. And that's 4 plus 5 times 0.2 plus 4, 0.1. And that is 4 plus, that works out to 1 plus 0.4. And that's 4 plus 1.4. And that's 5.4. So, and then let's also just figure out what is, let's see, so part D says find it exactly. So what is it exactly? So f of 0.2, 2.1 is exactly, just plug it in. So that is 2.1 squared e to the 0.2 plus 0.2. And if you punch into a calculator, blah, 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 you get about 5.59. So that was our approximation. 5.4, that was pretty good. Okay, now, separate that was side work. Okay, so now let's compare the old point with the exact point versus the approximation. So let's find delta F and delta L. So delta F is final F value which is 5.59, minus original f value, which from the given information was 4. That was 1.59. Now compare that with delta L. So delta L is final L value, which was 5.4, minus original L value, which is just the original Z value, which again is 4. And that's 1.4. Now let's find delta sub x of L and delta sub y of L. So those are respectively the amount of delta L that comes from the change in x, and then the amount that comes from the change in y. So let's take a look. Delta sub x of L. Now you could say, well, let's plug this into the formula. What's the formula? However, we have already calculated this in our calculation. Let's go back to the calculation of L from part C. First of all, notice that we already calculated delta L. It's written in our calculation. It is right here. We had our original Z value, and then we had the change from the approximation, which was 4, and then the change in the approximation, which is 1.4. But look at where 1.4 came from. It came from plus 1 and from plus 0.4. That first one is the change due to x. So delta sub x of L was just 1. Delta sub y of L is the final term in that calculation. Looking back over, that was just 0.4. Okay. And we can further identify stuff. What in this problem, what was delta x? Just bonus. What was delta x and what was delta y? Delta x was, again, it still already appears in our calculation. It's right there, 0.2. And what was delta y? It's right there in our calculation, 0.1. So it's all about identifying these changes and the role that they play in our calculation. That was a look at differentials and also how they relate to D statements. And also how they're connected is easy to see if we think in terms of linear approximation. That's also connected as well. There are lots of different connections between different ideas in this topic.